Hello and welcome to my talk. My name is Patrick Schiffer and I will now introduce you to our work on increasing feasibility in priority-based distributed trajectory planning for road vehicles. Trajectory planning with collision avoidance for a single vehicle can be modeled as an optimization problem, which is non-convex. And such problems are tough to solve in a computationally efficient way. To make things worse, I focus on trajectory planning for multiple vehicles at once. We call the group of all controlled vehicles a network control system, or NCS for short. So these vehicles are networked and autonomous, so we could construct the centralized problem formulation and have a central computer solve it. Unfortunately, the complexity of this problem grows exponentially with the number of vehicles. So we circumvent this problem by distributing the optimization problem to the vehicles, which reduces the problem size and therefore the computation time. I present a distribution strategy called priority-based, non-cooperative, distributed model predictive control. In this priority-based distribution approach, the priority assignment is a key factor for success. Priorities influence a number of properties for the NCS, which include the computation time, the feasibility, stability, and optimality, and the ability to avoid deadlock situations. While it is desirable to perform well in all of these properties, we always need feasible solutions that are ideally free of deadlocks. Unfortunately, finding a priority assignment that achieves only these two properties can already be a tricky task. Consider the example on the right, in which three vehicles are trying to follow a straight line and need to avoid an obstacle. And imagine the vehicles can only steer to avoid collisions and they must maintain their speed. So I'll give you a moment to assign priorities to the vehicles that result in feasible solutions. So you probably came up with this assignment, increasing the priority from top to bottom. So you see, we denote a higher priority with a lower value. But if I change the scenario now and added another obstacle, the priority assignment task now becomes infeasible. And we tackle this problem with dynamic priorities, so priorities which may change in every time step. And I will focus on two main questions in this talk. The first is, how should we choose priorities in every time step in order to obtain feasible solutions for each vehicle without running into deadlocks? And the second question is, how can we ensure that all agents can apply a feasible solution at every time step with dynamic priorities? And we call a process that fulfills this requirement recursively NCS feasible. There are many works that propose strategies on how to assign priorities. Most of them are from the robotics domain. A straightforward way to find the best assignment is to search through all possible permutations. This works in theory, but because the number of permutations is the factorial of the number of vehicles, it is too slow in practice. Another idea is to assign priorities randomly and then switch the priorities of pairs of vehicles. The priorities are only kept if the objective improves, resulting in a hill climb strategy. Several approaches can be classified as constraint-based, so they use a constraint-based heuristic. In those, higher priority is given to vehicles with less movement options. Some approaches assign priorities with heuristics aiming at a low objective function value. However, none of these algorithms is complete in the sense that they will always come up with an optimal or even feasible priority assignment. So we contribute to this problem with an algorithm tailored towards road vehicles, which was inspired by reference 4 here. And we further propose a process to obtain recursively NCS, so network control system, recursively NCS feasible priorities. This slide illustrates our conceptual process for distributed priority-based trajectory planning. It consists of 4 steps. First, vehicles plan the reachable path for the current time step and exchange that path with others. Second, we couple vehicles with intersecting paths. Third, we assign priorities for the current time step. And fourth, vehicles sequentially plan trajectories according to these priorities. So our priority assignment algorithm actually interweaves the third and fourth step, as I will explain next. Our algorithm assigns priorities one by one according to a constraint-based heuristic. We give higher priorities to vehicles that encounter more potential collisions. Now, I'll illustrate this with a simple example. Every vehicle plans its free trajectory, so meaning the optimal trajectory, without considering other vehicles and communicates it. That way, all vehicles can compute the number of their potential collisions with others. The dark blue and yellow vehicle have a potential collision in their free trajectory here. The vehicle with the most potential collisions plans first. So 2 vehicles tie here, so we choose the one with a lower unique ID as the one which plans first, which is the dark blue one. So now the dark blue vehicle has finished planning, and the process repeats for the remaining 2 vehicles. They plan their free trajectory, communicate, and count collisions. The yellow vehicle has most potential collisions and receives the next priority. The last vehicle now registers a potential collision with the yellow vehicle. It plans its trajectory last, and all vehicles move collision-free. However, as most algorithms for priority assignment, our algorithm might assign NCS infeasible priorities. So we need to ensure a safe behavior for all 8 vehicles. For a single vehicle, we achieve recursive feasibility by requiring the vehicle to stand still at the end of its trajectory. For recursive NCS feasible priorities, we propose the following reprioritization process. And I'm moving along the process diagram now to explain our process, which ensures recursive NCS feasibility. On the left side, if the proposed priorities for the current time step are infeasible, the vehicles return to the priorities of the previous time step and plan the trajectories again. So this step is not required for recursive NCS feasibility, but our experiments showed that priorities are often feasible for multiple consecutive time steps, which makes the step a valuable addition. If the previous priorities are infeasible as well, the vehicles reuse the input they computed in the previous time step and prolong the standstill at the end of the input trajectory by 1 time step. In every decision of this process, if we have NCS feasible priorities, we obtain a recursively feasible input trajectory. Independent of how we generated the input, so we achieve recursive NCS feasibility in our reprioritization process. This is the experiment environment in which we have tested our work. We have developed the CPM Lab as an open source platform for networked and autonomous vehicles. You can find out more about it at the website cpm.embedded.rwth-aachen.de or by clicking the link on this slide. In our experiments, vehicles travel on designated paths and adjust their speed profile to avoid collisions in a priority-based manner. You see 15 vehicles successfully avoiding collisions in this video with our priority assignment algorithm and reprioritization process. So now that you have an imagination of how the experiments are carried out, let's get into the details. In almost 40 experiments, we assigned priorities using 3 algorithms. Ours, which I call FCA, with the heuristic based on vehicles' potential collisions. One I call random, in which vehicles receive a new random priority every time step. And one I call static, in which vehicles receive only 1 priority for the duration of the experiment. We have embedded all 3 algorithms in the reprioritization process that I just presented. In an experiment, we have randomly assigned paths for all vehicles. And we have 1 designated start position for every vehicle. And in our experiments, we then increased the number of vehicles 1 by 1 and asked the question, can all vehicles plan deadlock-free trajectories for a minimum of 3 minutes? The maximum number of vehicles for which the answer to this question is yes is shown in a box plot for all experiments on the right. On the x-axis, you see the number of vehicles taking part in the experiment, and on the y-axis, you see the priority assignment algorithm. As you can see, static priorities performed worst. In the best case, only 11 vehicles could move without deadlocks for 3 minutes. Our algorithm, in combination with our reprioritization process, managed to assign priorities so that up to 17 vehicles could plan their trajectories distributedly. The random priorities performed about as well as the priorities based on our algorithm. One reason for this is that our reprioritization process, which allows replanning with previous priorities, promotes exploring different priorities. I have presented our priority assignment algorithm based on a heuristic which considers potential collisions. And we have proposed a reprioritization process which can embed any priority assignment algorithm and still guarantee recursive NCS feasibility. And we have demonstrated the effectiveness in experiments for distributed trajectory planning. Our experiments have shown that our reprioritization process promotes exploring new priorities. So adding this explorative behavior to heuristic-based priority assignment algorithms could therefore be investigated in the future. In the coming months, we plan to further research priority assignment algorithms for trajectory planning with a kinodynamic vehicle model. This was Patrick Schäfer from RWTH Aachen. Thank you for listening and enjoy the rest of the conference.